Hi, my name is Grace T. Ampoloquio. So, in this video, I'm going to discuss about fluid statics, specifically about hydrostatic force on a curved surface. Many surfaces of interest, such as those associated with dams, tanks, pipes, are non-planar. For example is the domed bottom of a bottle. Although the resultant fluid force can be determined by integration. General formulas can be developed. As an alternative approach, we will consider the equilibrium of fluid volume enclosed by the curved surface of interest and the horizontal and vertical position of this surface. So since we are talking about equilibrium, so there would be vertical and horizontal forces, the components. So in this figure, so if you have some curved surface underwater like this one, so this curved surface, let's label it A, and this would be letter B. And so in this curved surface, you can have a horizontal force, this FH, and also the vertical force, FV. So, if you combine them, you will get the resultant force FR. And also, you can find the angle of the resultant force. So, this will be the equation of the resultant force. And now the question is how to find the vertical and horizontal forces. So, these are the rules on how to find them. To find the horizontal force, project the curved surface onto a vertical plane and then use the rules previously discussed for vertical surfaces. So in this figure, it says in the rules that curved surface, project the curved surface onto a vertical plane. So this is the area. So what is the resultant force? We will know that in previous discussion of Sir Panorel that F of R is equals to gamma HC H sub C times area. So this will be the H sub C. So gamma times HC times area for the horizontal force. So next is the vertical force. It says that the volume of the fluid above the curved surface extending to the free surface, whether it's real or imaginary. Given the equation for Fv, or the vertical force, is the gamma times the volume of the fluid. So this is the free surface. So this will be the section A and this section B. So endpoint A all the way to the free surface, and also B all the way to the free surface. So this is the volume. So the force acts through the centroid of the area is somewhere here. So again, to find the vertical force and horizontal force, for horizontal force is to project the curved surface onto a vertical plane, and for vertical force is the force acting to the center of the area is the volume of a fluid. And to find the vertical force is that the volume of a fluid above the curved surface is extending to the free surface, whether it's real or imaginary. So let's take a look to this example. The problem is find the resultant force on the cylinder due to the water and find theta. Given the diameter is 4 feet, length is 1 foot, and the weight or the density of the water is 62.4. So this is the free surface and this is the free surface. So what we're going to do now is we need to get the horizontal forces and vertical forces. So we're going to make it in piece by piece. So let's make it point 1, point 2, point 3, and point 4. So it says that the diameter is 4 feet. And here, obviously, this is 2 feet. So first step is we're going to find the horizontal forces acting on this curved surface. So remember that in getting the horizontal forces, we need to project the curved surface onto a vertical plane. So at point 1, 2, and 3, we're going to project it here. So F of H from point 1 to 3 is equals to gamma H sub C times area is equals to 62.4 times 2 times 4 and times 1 is equals to 500 pounds. So next is we're going to find the horizontal force acting on this point 3 and point 4. So again, we're going to project the curved surface to a vertical plane. Here. So the horizontal force at 3 to 4 equals to 62.4 times 1 times 2 times 1. So this is equals to 125 pounds. Next step is we're going to get the vertical surface, now vertical forces. So, so in getting the vertical forces, we're going to extend the endpoints of each point. So first is the point 1 and point 2. We're going to extend the curved surface to the free surface. So here is the free surface. So we're going to extend point 2 up to the free surface. At point 1, no need. So this will be the volume. So to get the volume, in this area, so to get the volume in this area, so as you can see, there is a square. So we'll know that these sides are equal sides. This is 2, this is 2, this is 2, this is 2. And we'll know that the area of a square is r squared. And as you can see, there is a quarter of quarter half of a circle. So the area of this part is pi r squared over 4. So to get the volume in this area is to subtract the area of this part from the area of the square. So that is r squared minus pi r squared over 4. So the vertical force at point 1 and 2 is equals to 62.4 times r squared minus pi r squared over 4. So this is equal to 53.6 pounds. So next step is we're going to find the vertical forces at point 3 and 4. So remember that to get the vertical force is to extend the endpoints to the free surface. But in this case, at point 3, there is no free surface here. But there is a free surface here at point 4. But how can we extend point 3? So again, remember that in getting the vertical forces, we can extend these points whether there is real or imaginary free surface. So I'm going to use this part here, imaginary free surface. So this will be the volume. And this area is pi r squared over 4. So the vertical force at 0.324 is equals to 62.4 times pi r squared over 4, which is equals to 196 pounds. And last is the vertical force at point 2 and 3. So again, we're going to extend each endpoints to the free surface. So at point 2, here, and point 3 up to here. So this will be the volume. And as you can see, there you can separate this area. You can see it's a square. There is a quarter half of a circle. So to get the volume in this area is we're going to add the area in this shape, the square one, and in this one. So we know that the area is r squared, and add the area of this shape, which is pi r squared over 4. So the vertical force at point 2 and 3 is equals to 62.4 times r squared plus pi r squared over 4. This is 4. So this is equals to 446 pounds. So now we can now get the total horizontal forces and vertical forces. So in this part, this horizontal force is going to the right, and this is going to the left, and this vertical force here is going down, and this vertical force here of 0.3 and 4 is going up, and also here 0.2 and 3 is going up. So we need to get the total horizontal forces and vertical forces. So the total horizontal forces is equals to 500 minus 125, since this result is going to the left. So we need to subtract. So this is equals to 275 pounds. And the vertical forces are 446 plus 196 minus 53.6, since this result is going down. It's going to the left, going down. So this is equals to 558 pounds. So this horizontal force is going to the right and this is going up. So if I combining these components, we can get the resultant force here and also the angle theta. So Fr is equals to the square root of horizontal force squared plus vertical forces squared, which is equals to 697 pounds. And for the angle is arctangent 558 over 375 is equals to 57.5 degrees. So in this figure, this is the free surface. It's water here, water, free surface. So this is the center. This is the center. So the resultant force is somewhere here, which is almost 60 degrees. Here. Is theta F R. So the resultant force has to go through the centroid of this cylinder because there are different pressures here in this point, in this point, in this point, in this point. So in this part, here is the biggest or greatest pressure acting on this point. So it will be getting smaller and smaller and smaller and smaller and smaller until it gets zero. So it has to go along to the center, to the centroid here, this way. So that's all for the hydrostatic force on a curved surface. Thank you for watching and listening. Have a nice day and thank you.